I appreciate the opportunity to speak on behalf of the Precision Sustainable Agricultural team. We are an on-farm and on-station research network, part of PDI's efforts that brings together USDA, land-grant universities, farmers, commodity groups, and numerous agribusiness and tech partners. Farming is knowledge-intensive. Therefore, we need to understand how climate, soil, topography, and agricultural management interact spatially. We do this by reimagining the farm landscape as a living laboratory, coordinating networks of nationally distributed scientists around shared protocols, data acquisition, and communication. In our national on-farm research network of 180 farms and growing, we use intranet portals to standardize protocols and communication, and tablets and web-based applications that capture farm management history and standardize data acquisition across the team. IoT systems are perfect for on-farm research, as we can use low-cost technologies that allow us to capture extensive information about plant, soil, climate, and agricultural management. Now let's look at some examples of our data management system. Data management begins with a quality protocol that is tightly communicated to the technicians involved. We embed protocol and data entry together into one app. It includes everything they may need that day, such as material lists and site diagrams to conduct the project, and site-specific plot maps. Technicians can ask field management questions and have the app perform calculations to guide how data is collected. We enable constant checking back to ensure the technician is recording in the correct units, and further, we collect survey data all at the same time while we are conducting our sciences. Similarly, we provide tools for our technicians for the installation and quality control of IoT systems. Here we see a device set up for when they are installing soil moisture sensors. Nothing is more frustrating than setting up sensors and then driving back to your office to find it not collecting data. So while they are in the field, we can actually conduct tests to make sure data acquisition is working properly. We'll look at one of most recently from our sensor arrays, which includes the carriers of the data as it comes in, quality of the connection, and we can glimpse the entire data stream that is being sent to make sure all the sensors are operating before we get into the truck and head back to our offices. Monitoring of data quality can't stop there. We also maintain graphs of all the data, complete with diagnostic scenarios for when data doesn't look correct. Let's go back and look at one of the first IoT systems to enter the network. Here we are looking at volumetric water content from the site with sensors at different depths in the soil profile. Technicians can look at each of the sensors individually, make sure the patterns seem consistent with what they think it should have been for that location. We can zoom in to look at specific rainfall events. We can keep zooming in, and we can see the top sensor data collection and compare that to separate graphs of known precipitation amounts that occurred at those times. If anything looks inaccurate, we have the hardware diagnostic tools that see the performance of each piece of technology in the field. In addition to tools for the technicians, we now have tools for our data shepherds, whose job it is to look across the entirety of the network and look for missing data, examine the quality of the data coming in, and contact technicians when they notice data acquisition or aggregation is not working. These tools allow data shepherds to sort any of the factors in the database and graph what those might look like.
Lastly, we attempt to maintain automated analysis so that we can understand the trends going on in the data at any given moment in time, such as cover crop decomposition kinetics you can see in this figure where we're updating the K value. However, automated analysis is not sufficient alone. The data scientists still have to have eyes on the data to review model selection and parameters used. Automation also includes having the ability to understand trends associated with the spread of data we have coming in. Here are just two simple scripts that are very important for looking at our inference space. We would like to have as wide an array of soil types as possible, so we maintain a continuous graph of the soil types and the locations of each of the farms as they enter the network. These efforts permit real-time data acquisition and aggregation, quality control, and automated analysis and visualization for our growers and scientists. When we put this all together, we create an information ecology for precision sustainable agriculture that links up our science and data to inform insights in the form of decision support tools that further inform future research and farm practice. To date, we focus on water, nutrients, and pest dynamics, as well as environmental impacts and soil health. Finally, we actively monitor the farms, which feeds the data back into our databases, and thus creating the positive feedback loops necessary to feed the world in a more precise and sustainable way.